So, in the last couple of modules we have learned how to record steady state absorption and emission spectra, but then let us not forget that the purpose of this course is to learn how to make time resolved measurements, how to measure the rate constant of ultra fast processes. So, that is the direction in which we will proceed after this, but to do that it is important that we record steady state spectra first. Without that it makes no sense starting to do the time resolved experiment right away, because you do not really know then what kind of sample you are handling, what the energetics are, and so on and so forth. So, just to recollect what we have learned so far, the correct sequence of doing experiments is that you must record an absorption spectrum first, followed by emission spectrum, and then you must record an excitation spectrum. And you are happy if the excitation spectrum exactly matches a normalized absorption spectrum. If it does not, then either you have something interesting going on, there is ground state heterogeneity, or you have some impurity in the sample. Most of the time, unfortunately, the second case is correct. So, one needs to be careful even when we do seemingly mundane steady state experiments. Okay. That being said, let us come back to the question we had asked in one of the earlier modules. We want to follow fast processes, and we know how fast processes are in chemistry. The fastest process we have learned is expected to take about 170 femtosecond, and we had shown you some data from Professor Ahmed Zuel's work where they had actually taken snapshots of a bond breaking. But now suppose we want to do an experiment like that, suppose we want to follow a really fast process, how do we do it? That is what we are going to discuss today, how to follow fast processes. And what we will do now is we will restrict our discussion mainly to electronic levels, but it is not very difficult to incorporate vibrational levels into this, or to go over to completely vibrational levels altogether, right. That is what we discussed, how to follow fast processes. And this is something that we had shown earlier from Zuel's Nobel lecture of 1999, arrow of time. We had said that the capability of following ultra fast processes or fast processes has increased tremendously over the last few decades. As you see, in 1960s one could actually measure nanosecond, in 1950s one could measure microsecond, but 1960s onwards the journey towards picosecond and femtosecond and subsequently attosecond has been quite rapid. So, it is not very difficult anymore to measure processes that are in femtosecond time regime. So, we will start with that kind of an example. So, the first thing you need is you want to initiate a process by a pulsed excitation. We have discussed briefly what a pulse is. A pulse is light that goes on for a short duration and then goes off again. And here we typically work with femtosecond to picosecond, maximum nanosecond pulses. And when I say femtosecond pulses, I mean full width at half maximum is of the order of femtosecond. So, let us say I take a source of pulsed radiation and we excite whatever molecules we have using pulse excitation. How does the pulse, what does the pulse look like? Like this. If x axis is time, then the ideal pulse would be a delta function. What is a delta function? Yeah? Yeah, so it means that it has a delta function has a finite value only at one value of time or one value of x, and for all other values it is equal to 0. Okay? And of course, right now we are performing an idealized discussion. It is actually not possible to get a pulse that has absolutely 0 width, all that is relative. But for now, let us say that we have a capability of having a pulse which is a delta function, and you excite your sample with it. Now, let us think of what happens to excited state population. Before the pulse comes, is it possible to have any excited state population? No, right? What happens when the pulse comes? All of a sudden, this is the pulse, right? Let us say these are the two energy levels in the system. the pulse has come and we are going to call it a pump pulse, because what the pulse does is that it takes the system from this energy level to that energy level, right. So, that is a pump pulse. Now, what happens at the instant the pulse is on? At that instant, some molecules, depending on how strong the pulse is, some finite number of molecules would get promoted to their excited state, or in other words, at that instant excited state population is created and then the light goes off. What happens when the light goes off? Do all the molecules in the excited state come back to the ground state at that instant? Do you think that would happen? That would not happen. So, what happens rather is that the excited state population decays over time. This is sort of like nuclear decay. You know that radioactive nuclei decay to more stable nuclei as and it is a first order process. Now, they are left to decay by themselves, it is a first order process by which they decay. Here also what we have done essentially is that we have created an excited state population and we have left the molecules there to decay by themselves. So, this decay in the simplest case scenario is going to be a first order or exponential decay. The question is, how do I follow it, and how do I follow it with femtosecond time resolution? Do not forget, our purpose is to study things in femtosecond time scale. To do this, what we do is, let us consider this is your sample, this square right here. Let us consider this is the pulsed pump light. We need a second pulse to follow the time evolution of the excited state. That pulse is called a probe pulse. And the pulse, let us say for now, is such that its energy exactly matches an absorption of the excited state that is created by the pump pulse, alright. And what we do is, we detect the intensity not of the pump light, but rather the probe light, okay. Let us say I have a detector here, not here, here. Then I will be following the intensity of the light that passes through, the probe light that passes through the sample, right. And what we have learned in steady state absorption spectroscopy is that when we look at intensity like this, it makes sense to talk in terms of absorbance, epsilon CL. And the advantage of working with absorbance is that, of course, it is proportional to concentration. So, now see this red light, the probe light, is absorbed by the excited state and not by the ground state. So, if I work out absorbance of the probe light, then I get to know the concentration of the excited state, isn't it, right. So, whatever absorbance value I get at time 0, that should be able to give me a measure of the concentration of the excited state produced as a result of instantaneous excitation, okay. Now, let us say I delay the pulse probe light with respect to the pulse pump light, and that can be done very easily. Let us say we have a pump source and we have a probe source. Of course, light we have to reflect light using optics, right, and mostly in femtosecond time regime we do not want to use lenses, we as far as possible we want to use mirrors. Let us say, and we are going to go to the lab and see it for ourselves, let us say that we have given some kind of a path difference to the pump or to the probe, and let us say the path differences are exactly the same to start with. The pump and the probe lights appear at the sample exactly at the same time. Then what will happen? The probe light is going to interrogate this situation. That time at which the path difference between pump and probe is 0 is called time 0, okay. So, that is what the probe light is going to interrogate. It is going to tell us what is the population of the excited state at the instant of excitation. What happens if I change the path length a little bit? Suppose the path length to start with is such that the probe has reached the sample before the pulse. Then of course, there is no excited state population and absorbance for the probe light is 0, and that is the situation at this point in time and this point in time. Then when time 0 is achieved, then all of a sudden we see a strong absorbance, because at that instant the excited state population has been created. Now, if I keep on changing the path length of the probe light, now suppose the probe light reaches the sample after the pump light, say at this instant, what will happen? By that time, the excited state population would have decreased from here to here, right. So, in this expression C would have gone down and correspondingly absorbance would have also gone down. So, what I get here is that I get a decreased value of absorbance of probe light. Remember, we get a decrease in the absorbance of probe light that is proportional to the decrease in the excited state population in that time. So, if I keep on changing the delay of the probe light, then it is going to come later and later and later compared to the pump light, and it is going to interrogate lesser and lesser population of the excited state. Correspondingly, absorbance will go down, and now the plot that you get, what is shown as these big circles in this diagram, the plot that you get is exactly of the same shape as the plot of decay of excited state population with time after excitation by pulse light. Are we clear? Okay. So, this is how one can follow the dynamics in time by giving a path length. Now, let us do a quick little bit of math. What kind of path length do I have to give in order to get, say, 1 femtosecond time resolution? So, to do that, it is useful to remember something that is very easy. Light travels 1 foot in 1 nanosecond, and when I say 1 foot, I mean 30 centimeter, right. That comes quite easily if you know the speed of light, and you agree with me that 1 foot is approximately 30 centimeter. All right. So, how much time does it take for light to travel 1 micron? Can we work that out? Or maybe 3 micron. How much time does it take for light to travel 3 micron? Light requires 1 nanosecond, 10 to the power minus 9 seconds to travel 30 centimeter. So, to travel 3 micron, how much time is required? 1 femtosecond, is that right? Or 10 femtosecond? We have two answers. Remember, 1 centimeter is 10 to the power minus 2, 10 femtosecond, not 1 femtosecond, right. So, if I can give a path difference of 1 micron, then that is equivalent to 10 femtosecond. Is it easy or is it difficult to mechanically produce a path length of 1 micron? So, when I say mechanically giving a path difference of 1 micron, what I mean is that the light will come and strike a mirror, let us say, then I will move the mirror forward by half a micron. Then the path difference that will come of the light that is being retroreflected, let us have 2 mirrors actually, one mirror like this, one mirror like this. Light comes, hits this mirror, comes here, goes back. I move this assembly of mirrors by half a micron. That is equivalent to 10 femtosecond time delay, right. And then the way we always give time delay is that we are going to see it in the lab, we mount this whole thing on a screw. So, we have to just turn the screw very minutely, so that the linear displacement is less than micron. That is very easily done actually. So, it is not very difficult to achieve femtosecond time resolution by giving path differences of a micron or a less. We are going to come back to this when we discuss maybe femtosecond optical gating, but the technique that we have discussed in a very preliminary manner here is called femtosecond pump probe technique, and most of the ultrafast studies are based on some variant of this technique or the other, right. If you come back to this, this is the data that I showed you earlier, snapshots of bond breaking. Here also what Zuel's group had done was that they used a pump and they used a probe, but then they did something more. They used very short pulses, so they could do what is called they could excite a wave packet and they could look at wave packet dynamics. That is why they could see oscillations like this. We will come back to wave packet dynamics when we are a little further into the course. But before that, let us ask a simpler question. We are saying that we are going to create an excited state population, fine. but we create an excited state population and then the molecule comes back to the ground state, that is not much of a fun. At most we measure the excited state population, but then what will we do with that number? The question that we want to ask is, can we initiate some chemistry, some chemical reaction by using these pulses of light? And the answer is yes. How would you do it? Suppose I have some photochemical reaction by which I excite a molecule and the molecule gives out protons. This phenomenon is called photoacidity. That is what we are going to discuss now. Now suppose we take that molecule, a photoacid, which gives out protons when excited by light, but this time we excite it with pulse light. What will happen? We will get a burst of photons coming out of the molecule when the light pulse hits it. So within the pulse width, let us say we have a 100 femtosecond pulse, within those 100 femtosecond we would have created a certain concentration of proton in the vicinity of the laser, light spot that is incident on the sample. Okay. So we can create bursts of protons this way, and then suppose we have some acid catalyzed reaction. We can initiate that acid catalyzed reaction with femtosecond time accuracy if we release the protons by using a femtosecond pulse, right. The question is, why is it that protons will be released in the first place as a result of irradiation with light? To understand that, let us go back to some fundamental photochemistry and let us recall that reactivity in excited state is actually not the same as that in the ground state. Why is that so? Before we go to that, let me ask a very simple question. In chemistry, what is it that determines reactivity? What is it that determines how a molecule will react? And easy. Well, bond strength, yes, but something more fundamental, electron configuration, isn't it? Okay, forget molecules, go back to atoms. What is it that determines that sodium is going to give up an electron and become sodium plus? What is it that determines that chlorine likes to take up an electron and become chloride? It is electron configuration, right? In chemistry, we know that electron configuration determines reactivity. And what we now need to appreciate is that electron configuration is different between ground state and excited state. That is actually obvious, but sometimes even the obvious has to be restated. So let us look at this simple diagram here. Electronic arrangement is different in the excited state than in the ground state, right? So let us see what is electronic arrangement in the ground state. In a very simple organic molecule, no unpaired electron, no nothing, we can draw it like this simply. There is a more complicated picture, but for now we can live with this, right? We have a doubly occupied HOMO, highest occupied molecular orbital, and of course an empty lowest unoccupied molecular orbital. Now let us say we perform a HOMO to LUMO excitation, okay. So in this case, before the excitation, in the ground state, this ground state is called singlet ground state S0. What is the electron configuration? If I denote HOMO by small h and LUMO by small l, H2 L0. Now let us say I performed a HOMO to LUMO excitation. Now what is the configuration? H1 L1. So configuration is different. If configuration is different, reactivity can be different. I am not saying that it has to be different, but it can be different. That is first point to take home. Second point is that this is not the only way in which your excited state can be formed. It is not necessary that your excited state is going to be a singlet. It can be a triplet also. And once again, triplet excited state actually has a little more profound meaning, but for now we can live with this. Okay, and triplet state, as I think we know, has T1 has a lower energy than S1. Okay, we will not discuss why. We have discussed this in a little more detail in our molecular spectroscopy course. Right. So the point is that electronic arrangement is different in the excited state than in the ground state. So reactivity might be different. Okay, that is a general discussion. Now let us go to a little more specific discussion. Let us talk about the problem that we introduced a little while ago. photoacidity. It is a general rule that organic acids, I have written acids here, so I do not mean sulfuric acid, nitric acid, perchloric acid, I mean organic acids. Organic acids are more acidic in excited state, organic bases are more basic. To explain this, let me once again ask a question, the answer to which is known to everyone. Let us take an example of an organic acid. The first example that comes to my mind, of course, first example that comes to your mind could be carboxylic acid, but let us talk about phenol. Phenol is acidic, strongly acidic or weakly acidic? It is a weak acid, right? We will shortly discuss what the pKa is for at least one phenol. Why is phenol acidic? H plus release. Phenoxide ion that is formed by release of H plus is stabilized. How is it stabilized? I do not want to use resonance because resonance is a valence bond, I mean resonance is a tool by which you extend valence bond theory to more than beyond 2 center 2 electron system, and the problem is yes, and the problem is that it does not allow me to access excited state. So let us talk about molecular orbitals. Okay, delocalization is something we can live with. Now let us think a little bit. We have phenol, we have proton has gone out, so you have the phenoxide ion. So let us not think in terms of those electron pairs or anything, let us think in terms of an electron cloud on oxygen. Okay, an electron cloud on oxygen is not a happy situation, if it can get delocalized it is better. So now if it has to get delocalized in the same molecule, it has to be accommodated in some molecular orbital. What is the molecular orbital that is available? The unoccupied anti-bonding orbitals. Okay, if you go back to the simplest example of phenol, a benzene ring and OH, then I think we remember the energy level diagram for benzene, right? 3 bonding MOs, 3 anti-bonding MOs. So one of those 2 degenerate anti-bonding MOs is the lowest energy molecular orbital available to accommodate the incoming electron cloud from oxygen. Okay, and that is what happens, that is why phenol is acidic. Now think we have performed a pi star excitation, HOMO to LUMO excitation. Now what will happen? Now you create a vacancy in the lower energy bonding orbital, right, and now the incoming electron cloud from oxygen can happily reside in the lower energy bonding molecular orbital, it does not have to go to the higher energy anti-bonding orbital. That is why it is a happier situation. Okay, and that is why phenol is more acidic in the excited state than in the ground state. Okay, and you can build a similar argument for things like aromatic carboxylates, which are bases. They also become stronger bases for similar reason. This is discussed in any standard photochemistry textbook. Okay, now I have proposed something, but there is no reason for you to believe what I am saying unless I show you some experimental proof, and here we are showing you an experimental proof. This discussion is available in Lakovich's Principles of Fluorescence Spectroscopy book. What I am showing you here is absorption spectra of beta naphthol at different acidities. Okay. So first one is this black line denotes absorption spectrum of beta naphthol in 0.1 molar HCl, very strongly acidic. So we can safely say that this absorption spectrum, oh that was a little bit of a giveaway, this absorption spectrum at high acid concentration is that of undissociated beta naphthol, yeah, beta naphthol, no naphtholate is there. Now look at the spectrum that is in dashed lines, that is for beta naphthol in presence of 0.05 molar sodium hydroxide, and it is distinctly different from the absorption spectrum that we have for your highly acidic solution. Why is that so? What is the species of beta naphthol that is going to be there in an alkaline medium like 0.05 molar sodium hydroxide? Beta naphtholate, proton is not there. Okay. So now we know our alphabet. This is the absorption spectrum of naphthol. This here, the red shifted one, is the absorption spectrum of naphtholate. Now look at the situation at pH 3. Can you even see the absorption spectrum of beta naphthol at pH 3 in this diagram? If you look very carefully in this region, you see some dots, right. You do not see it because it is so nicely overlapped with the absorption spectrum of beta naphthol in highly acidic solutions. What does that mean? That means at pH 3 there is no naphtholate, it is beta naphthol all the way, right. Now let us look at the fluorescence spectrum, emission spectrum. This here is the emission spectrum of beta naphthol at pH at highly acidic concentration. So we can safely say that this spectrum is for undissociated beta naphthol. This spectrum here is for naphtholate because it is in highly alkaline solution. Now at pH 3 you see the spectrum that we get, the emission spectrum, is not exactly what we get in the highly acidic solution. Rather you get a shoulder that more or less matches what the emission spectrum would have been in highly alkaline condition. What does that mean? The absorption spectra tell us that at pH 3 beta naphthol is completely undissociated. Emission spectra tell us that in emission we get signature of some naphtholate at pH 3, but in ground state there is no naphtholate. Where did this naphtholate come from that is emitting? It must have come as a result of excited state dissociation or photodissociation of beta naphthol, alright. So it seems that photoacidity is real. At pH 3, even though there is no beta naphthol at ground state, everything is, all molecules are in naphthol form. Some of them actually lose proton in the excited state to give you beta naphthol, signature of which is obtained in the emission spectrum. Okay. So photoacidity is qualitatively demonstrated. Now let us see it in a little more quantitative manner. So using absorption spectrum you can construct a titration curve. Inflection point of that curve is going to give you the pKa in the ground state. If I do a similar exercise using emission spectrum, again I will get a pKa. Will that pKa be of the ground state? No, it will be of the excited state. So let us see what these titration curves look like. These are the two titration curves. For the ground state, you see pKa turns out to be 9.2. As you said correctly, it is a very weak acid. In the excited state, pKa turns out to be 2. And remember, pKa is log of hydrogen ion concentration, hydrogen ion activity. So when we go from 9.2 to 9.2 to 2, we are saying the change in concentration of protons is from 10 to the power minus 9 to 10 to the power minus 2, 7 orders of magnitude change. So photoacidity is actually a is not something that is very trivial, it is a strong effect. Okay. So now if I take the same beta naphthol and I excite it using pulse light, what will happen? The moment the pulse light is incident on the beta naphthol solution, we will get a burst of protons coming out. Now if I want to follow the kinetics of any proton mediated process, proton catalyzed process, acid catalyzed process, then I can do that, right. First of all, I can even work out the time it takes, if I can, for the beta naphthol to form, naphtholate to form from beta naphthol post excitation. All I have to do is I have to do a pump probe experiment using probe in this region, alright. We are going to talk a little more later on about pump probe spectroscopy, about the different kinds of signal. Today is only an introduction. So we could actually follow the dissociation of this, but more interestingly we can also follow the kinetics of processes that are triggered by this burst of protons that we have released. In fact, this kind of an experiment has been done. In 2003 the first paper was published in Science. What you see here, pyranine, this is a very strong photoacid. When you excite it, proton comes out, and a base that was used is acetate. Using a UV pump, proton was liberated from pyranine, and using an IR probe, I think we all know what IR spectroscopy is used for. IR spectroscopy is used to identify functional groups in a molecule, right. So, in this example, when proton goes out, what will happen? This OH stretch is going to go down with time, and then here this acetate OH, this will come up with time. So, that is the experiment that is done, and once again we will come back and discuss this experiment in more detail later on, but in a nutshell this is what the kind of data you get. You see a rise in absorbance, which is which signifies protonation of acetate, and with a little more closer analysis of the data, what was done by the group of Nibbering and co-workers is that they could work out the mechanism of reaction between an acid and a base. All of us have studied in school that acid base reaction is very fast and you cannot define the mechanism. That is not true any longer. I mean, it has not been true for 12, 13 years now, 14 years, because the mechanism of acid base reaction has been worked out using ultrafast UV pump or visible pump IR probe experiments. So, that is the kind of information you can get from ultrafast pump probe experiments. Okay. So, this is our introduction to how to follow ultrafast processes. Next, we are going to move on to see how you follow dynamics of fluorescence in hundreds of picosecond to hundreds of nanoseconds using a technique called time correlated single photon counting.